Gentlemen, please recall, we're done with satellites and Kepler. We are starting the next topic. We've only got 2 weeks. Less Friday, less Monday that I just spent finishing up satellites. I will probably try and find a lesson for you to watch over the weekend, and it might link Friday's lesson, and then on Monday, whatever email I send you, please make sure you watch it and treat it as a lesson. I want to try and reclaim one of those missed lessons. So, also, if you did the Kepler validation, please just leave it at the end of the lesson. I'll grab it, I'll mark it, and give you feedback. We are now on to a torque. Torque is a turning effect that can occur if your force acts not at the centre of an object. If you apply a force to the centre of an object, it will move it translationally. It will move it left or right or up or down or forwards or backwards. If you take that object and you move your force away from the centre of mass and then apply the force, it's now going to cause the object to rotate. Okay? So it's going to make the object move about a common point called a pivot. Foster, anything? No? Cool. So, we're going to be using it is a vector in the sense that it has a direction. The direction we will be using is clockwise or anti-clockwise as viewed in any diagram provided. Okay? Please do not abbreviate, and I will try my best to write out the full word clockwise. Don't write CW. Well, actually, you can actually abbreviate, but yeah, I'll show you where you're allowed to abbreviate. So, let's jump straight into the equation. The equation for torque is R times F. Now, let's get a diagram down, please. Over here. Now, I always get a bit cautious that I am not screen capturing, but I'm certain we are. Yes, we're good. Over to the right. What is it doing? Why are you... Go away. Like, why is it bringing up that? Right. Gentlemen, I'm going to place a diagram. Over here, could you please draw? Not 2 lines. Thank you. 1 line. There he is. Could you draw the following item? Please. Oh, what the hell? Are you serious? Are we seeing what I'm seeing? Why is it doing that? What just happened? Why? Oh my god. Oh my god. Oh my god. What the heck is happening? All I want to do is draw my Sidchrome 10mm spanner, for God's sake. Now, I'm going to highlight the center of that and call it a capital P, which stands for pivot. You need to identify the pivot in any diagram if it is not already. We're going to draw then a dashed line to where we apply our force. This dashed line is known as the line of action. It is the distance from the pivot to the force. Okay? And what we wish to have is the perpendicular component of the force, which is the force, the component of the force to the line of action. Now, why has that occurred? I can no longer... no, I want to go full screen, and I'd like to... Thank you. Some weird stuff going on here today, children. There's my perpendicular force. Okay? So just get that written down. So our equation is torque equals R F perp or R F sine theta. Gentlemen, theta is always the angle between the force and the line of action. Between the force and the line of action. It will make more sense as we finish this page. Always take the angle between the line of action and the force as your theta. Okay, so let's just quickly sketch a very simple diagram. Here is a force. I wanted that in blue. Blue. Here's my force. Here is my line of action. Okay, now it doesn't matter that I've drawn that slightly tilted. There's R, there's theta, and here is F. If I wished to sketch in F, then I could do the following. I could sketch in the perpendicular. I could make this angle here, call it phi. All right, which is the perpendicular component, and that would be F cos phi. Or what else could it be? F sine theta, which is what I told you to write at the start, R F sine theta. So, again, the perpendicular component can be determined from the angle that's not involved in the perpendicular component. All right, it's always going to be R, it's always going to be F sine theta. So let's just put in an example. R equals 1 meter, F is 100 newtons, provided at an angle of 45 degrees. So we'll go torque equals R F sine theta, 1 times 100, I don't know why I put that in brackets, sine 45, and we get 70.7 Newton meters clockwise. Okay, so those are our units. You basically just take the unit from force, multiply by the unit from distance. Please be aware, in work, the transfer of energy, that's a force acting translationally over a distance, and that is a Newton meter, which we call a joule. This is not a unit of energy. It is a unit of rotational force. Okay? Do not try and simplify it. Do not try and write capital J. Okay? It is not the same, even though it has the same dimensions. It's a little bit tricky, but just write it as Newton meters. And I have not spelled the word clockwise correctly. Let me try again. Oh, great. Thank you. That goes away. Yep, cool. Sorry. That's a little bit better. Okay. Now, perpendicular force is probably used for about 90% of the problems and the scenarios. However, there is a perpendicular distance example, which, as I said, can be used. There are some questions where perpendicular distance is easier. It's not often, but I'll show you some examples where it is much simpler. What we do for perpendicular distance, let's just draw in our pivot force. Let's just draw in our pivot point. Let's draw in our line of action, and let's draw in a force like so, okay, with an angle that was in black pen, I promise you, theta, okay? Now, again, we could draw in the perpendicular, but what we do here, sometimes, if you extend your force either direction, you will get to a point where you can draw a right angle to the force vector. And I didn't actually have to extend my force. Sometimes you have to extend the force diagram. This now becomes R perpendicular, which is the perpendicular distance to our force vector. It's not as visual. I mean, we should be able to visualize looking at the force and then considering the component of the force that acts at 90 degrees. Yes, we can see that. It makes sense. This one's a little less intuitive. That why would you want to find the perpendicular distance to a force is not a thing, but we draw it. Either way, we could say here that R perp, well, have a look. We've got R is the hypotenuse, R perp is the opposite, so we do the opposite, R sine theta. Okay? So look what we've got. We've got torque equals R perp F equals R sine theta F. it does not matter whether we have the sine theta attached to the f, finding f perp, or the sine theta attached to r to find r perp. If you always use the angle between the force and the line of action. If you stick with that rule, you cannot get it wrong. It's just RF sine theta. It rolls off the tongue. You got theta, you got R, you got F. You got a door, you got a gym. Randy Couture taught me that. Okay? Former UFC heavyweight champion. It was a meme about 5 years ago. Clearly your kids are not up to date with your 2014 memes. Here are a few quick diagrams. The first one makes now. The easiest example here would be to open this door requires a certain amount of torque. If I was staring down at the door, it would be an anti-clockwise torque. The door needs an anti-clockwise torque to open. I apply a force with my meat hooks a certain distance from the pivot. The pivot point is where the hinges are. So if I want to maximise my torque, I would pick the greatest distance from the hinge to apply my force. That way, if a torque is constant, if R is increased, then the required F goes down. If I was to try and open the door, like in this diagram here, close to the pivot, if I minimise my R value, I have to increase the force. Next time you're at a door, try and open it by pushing about 10 centimetres from the hinge. You're going to look very, very strange. You know, it's going to take a lot more force. It's a very stupid thing to do. The large torque is if we can increase our leverage. If we can increase the line of action, then we can either increase our torque, or if torque is constant, then it decreases the required force. 4-mark question on why door handles are placed at the opposite side of the hinge. Waste question 2019. Here's our force. Again, this would be silly. That would be me trying to open the door by pushing the door handle at an angle of 45 degrees. It's silly because only a certain component of my force is actually perpendicular. The other component is literally pushing the hinge out of the frame. I don't want a translational force when I open the door. I want a rotational force. So I don't want to pull the door away from the hinge, nor do I want to push it towards the hinge. I want to push it around the pivot. Here is where, if you wanted to determine R perp, you would extend your line of action, you would extend your force until you found the perpendicular distance to the pivot point, okay? So, that we will look at some examples as we get through the course. Centre of mass. Obviously, objects have volume, and depending on where you apply the force, different things would happen. As I said before, if your force is applied towards the centre of mass, you're going to move it translationally. If you apply a force away from that, it's going to start to rotate. Now, if we want to find something, the centre of mass of a two-body system, we already looked at that. The barycenter of two lumps of rock, Julian and Robert. It's in the middle, and it's just going to be x1, m1 over the sums of the masses. If we had more than two bodies, we just continue to add these terms, m and x. What we will find is an example hopefully will make more sense. Let's draw a lump of wood. And so I'm going to use my lovely wood lump colour. There's my lump of wood. Okay. Let's suspend one side on a support such that it would want to pivot. So I'm done with my lovely wood colour. Oh, Jesus. I need to set up all of my... So there is my pivot point. Now, for this to make sense, let's slice my lump of wood into 10 centimetre intervals. And so each 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's 1 meter long. Right? And each 10 centimeter interval, I could draw in the weight force acting for that 10 centimeter lump of wood. Obviously, my radius is going to increase for each lump of wood further from the pivot. Okay? So R going all the way along. The first R value would be 0.1. The fifth R value would be 0.5. Does that make sense? Now, you will be given one of these key words. Uniform mass, uniform density, or homogeneous. Any of these terms is telling you that its center of mass is said to act directly midway along. Okay? So center of mass acts at halfway along its length. If you are given the term uniform mass, uniform density, or homogeneous mass, it will be appearing all over the place as we go through this course. Okay? So it's going to be half of the length. One other way to look at this is to consider the torques acting. I'm going to draw in the magnitudes of the torque as we go along. So we've got 1, 2, 3, 4, 5, 6. Don't draw this in. 9, 10. Obviously, the further along you get, each unit of mass is going to produce a greater torque because it is acting further from the pivot. Yes? So, what we do is integrate from 0 to L of blah, blah, blah. Where along could we find that an average object produces an average torque? Hey, it's in the middle. If it's uniform, in the middle. If it's non-uniform, we can find it. All right. But basically, from this diagram, we would basically slice this midway along and go, where would an object be such that it could produce this torque? It has to be in the middle. Okay? It's not the best definition, but there's a really cool experimental technique. If you have an object, you can determine its center of mass. Watch this. If I took a non-uniform object, like so, that maybe was a little bit more denser over here. Maybe the center of mass, which we draw as a little circle with a cross, maybe it acts over here. Okay? Its weight force acts there. If I was to pinch my object over here with my thumb and broken... No, that's all right. There we go. Then I'm essentially setting up a pivot. From the weight force, there is now a line of action. There's an angle between, and a torque would be produced. Nailed it. Now, I take my non-uniform mass, where its center of mass, I'm lying, this is uniform mass, uniform density. If it was uniform density, then I know that it's going to be halfway along the width, halfway along the depth, it's going to be smack bang in the middle. I could draw it fairly confidently. But if I didn't know it's uniform, I didn't know its center of mass because it's non-uniform, I pinch it somewhere. And then I allow that torque to act. So we allow it to sort of hang down like so. All right. Now, I know now it's positioned itself so that there is no net torque. The only way that can occur is if the weight force is acting directly beneath the pivot. What that does is it sets the angle between the force.
0.
No. 180. At 180, there is zero torque. So, try and draw your best. Draw your object now so that the weight force is down here directly directly beneath, my bad, the pivot. Okay? So, there's your scenario, 180 degrees, torque equals 0. So, you take your non-uniform, non-platonic, heterogeneous solid, you allow it to hang beneath a pivot, and you draw literally a line straight down. Alright? I now know that the centre of mass lies somewhere along that line. I then go and pinch it somewhere else. I allow it to hang, okay, like so, and then I draw, again, a vertical straight line. I now know that the centre of mass now also lies somewhere along that line. Where they converge, that's where the centre of mass is. I could do it one more time, over here, okay, and then I bent it by a bit more in the previous one, but if you do it properly, and you hang it from a retort stand, we've got bits of plastic perspex of different sizes, and they've got little holes around the perimeter, and you basically hang it on a hook, and you draw a straight line down, and then you move it, and allow it to rotate, and then you draw a straight line down. You can do that for any object. It doesn't even have to be 2D, it could be 3D. No, actually, no, tell a lie. Can't really. 2Ds, flat pieces. Now, let's take everything that we have learnt so far this lesson and draw a steel beam of uniform density. Okay? And I'm going to now give you some values. Let's say that our pivot point here, it's going to pivot about the contact point at an angle of 40 degrees to the horizontal. We will say that it has a length of 5 meters, a mass of 100 kgs. I'm going to, again, if you have to be told that it is uniform mass, uniform density, and now we can say that R equals L on 2 equals 5 on 2, 2.5. Okay? Now, this is one little trick that can occur. We've been given the angle to the horizontal. We want the angle between the vertical and our line of action. Okay? And that's obviously 50 degrees. If you wanted to visualize what weight perp is, it's not the best. Oh dear, I'm back in steel beam mode. The line of action would look like that. You don't need to draw it, but that's what it looks like. And hey, that would be, I don't know, weight cos 40 or weight sine 50. Always take the angle between the force and the force and the line of action. Always take that 50. Okay? So, we would write out the following. Torque equals RF sine theta equals L on 2 bracket mg sine theta. Okay? Don't risk it. Put in one extra line. Show all you're working out. 5 on 2. We get 1,880 Newton meters clockwise. Okay? Now it didn't really visualize it, but I was in F perpendicular mode. I said, look, at this point, that line is the perpendicular force, and its magnitude is 980 sine 50. That's it there, right? So there's my sine theta attached to F. We could do the perpendicular. Again, it's not necessary, but I want you to be familiar with the perpendicular distance. That was R. R is the distance, line of action from pivot to where the force acts, okay? If I was to extend my weight force down, then my R perp is there. Yeah? That's the perpendicular distance to my force. If you looked at that diagram and said, how could we express R perp? You'd go, well, that's R sine 50. Okay? Which is L on 2 sine 50. So over here, I could do the R perp F equals L on 2 sine 50 times 100 by 9.8. See, all I've done is I've shifted the sine 50. It's no longer attached to force to determine perpendicular force. It's now attached to R to find perpendicular distance. I didn't mean to do that. Please go back. Thank you very much. We get the same value, 1880 Newton meters clockwise, okay? As I said, 90% of the time, perpendicular force is the easiest way to do this. Okay, now we're pretty much done. Come on, I want you to zoom out. There we go. Have a read of that in your own time. Why was my Fitbit Connect? Okay, fair enough. It was just there when I made the screenshot. Fair enough. Don't ask questions. Homework, gentlemen, please do these questions. They are easy. What we've just learnt then, R, F, sine theta, torque. You've got 4 variables. It'll be, you've got 3 variables, determine the 4th. Okay? It's that easy. So please, do these questions. We've got 20 minutes left. I want to jump into the next section where it gets a little bit trickier. Okay? So normally we would stop the lesson here, Brendan. Normally we'd stop the lesson here. I'd let you do these questions. It's for homework. Sorry, I want to check them on Friday that they're done. Oh, hello. Why? Okay, thank you, keyboard. No, you can go away. How long was that there for? That's weird. Strange. Strange things. Strange things. Okay, over the page, please. This is where things get trickier, so please pay attention. If an object is at rest or not accelerating, there are 3 types of equilibrium that it is in. At the moment, you've learnt 2 of them. Oh, now there is a typo here, and I'll get to that in just a moment. Sorry about that. You are in vertical translational equilibrium if you are not accelerating up or down. Cameron. So we've already learnt that. That is sum of all forces in the y equals 0. I.e., sum of all forces in the y equals 0 equals weight plus tension plus, Fr. We've already played around with that. We are also in horizontal translational. That just means that we're not accelerating left or right. That is sum of all forces in the x. The next one that we're adding to this is rotational. It means that you are not accelerating in a rotational or about an axis. You're not starting to spin. You are not starting to fall. The bridge is not collapsing. The ladder is not sliding. You are not falling out of your chair. All right, you are static. Static is easy. The maths is easy, year 12 level. If you want to look at rotational dynamics, it gets trickier. The equations of rotational velocities and momentums and energies gets a little bit trickier, and it can be done in tertiary university courses. But there is a way to write this down, and I'd like you to follow my lead up the top. You say that the sum of all torque equals 0. That means that the sum of your torque clockwise equals the sum of your torque anti-clockwise. If an object is at rest, if there's any torque clockwise, wanting it to rotate in a clockwise fashion, there has to be an opposing counter-clockwise or anti-clockwise torque balancing to prevent any acceleration. Now, what we call it is a clockwise moment equals anti-clockwise moment. Oops, there's an M there. Underneath, just quickly write clockwise moment. A moment is the sum of all torques in that direction. Okay? So if I had, 3 masses on a plank, and those masses from one side of the plank, they're producing for you, let's just say it's a clockwise torque. Each of them are producing a clockwise torque. The clockwise moment is the sum of that torque plus the sum of that torque plus the sum of that torque. You literally quantify them, add them together, boom, that is my moment. Okay? So be careful. I'm going to force you all to write a blurb at the start of each question, and you're going to get so sick and tired of writing it, but it's worth a mark. There's a mark for writing those statements at the start of each question. Okay. Consider, please, this beam. For now, negligible mass. That's good. That means no torque produced. Okay? Now, I'm going to set up a scenario that a Year 7 student could do in the Year 7 class. But we're going to attack it at a Year 12 level. So, let's consider, thanks, 10 kilos, M1. They might not look the same size, but maybe they've got different densities. Or maybe I just picked the wrong side to draw this. And let's just say R1 is going to be this distance to here. And R2, let's give 5 meters. That distance to there. And we're going to analyze that that's the pivot point. Okay. In fact, that is the point at which the object would be stationary. It's not moving. Now, I'm just going to draw in the weight force. We'll call that weight 1. We'll call that weight 2. There is a third force acting on this beam of negligible mass. It's not the weight of the beam because it doesn't have any mass. Where do you think the third force is to keep this in vertical translational equilibrium? Yes. We'll call it the reaction force. Okay? So, at that support, the support is pushing up. Have a think. If that upwards force didn't exist, this object would be falling downwards at a rate of 9.8 meters per second per second. Now, step 1. We always solve first that the sum of rotational torque equals 0. We will say that torque equals RF sine theta. We will say that the clockwise moment equals the anti-clockwise moment. And we take pivot about P. In some scenarios, there might be different points where you could analyze your pivot. And if it is not identified on the diagram, you need to draw it in. Okay? So please, if it's not there, label it, put a dot, and call it capital P. From there, we would put in these values, but keep our subscripts. So we would go R1 M1G sine theta equals R2 M2G sine theta. All right, that is the torque produced by mass 1, a distance from the pivot, the force at a certain angle in a certain gravitational field. Now, the end game is we didn't have R1, so really, I should have told you, at what distance must we place this 10 kilo mass to balance the 20? The Year 7s would look at that and go, all right, you've got double the mass, must be half the distance. The answer is 2.5. You know, bring this in closer, that one's further out, you do your mechanical advantage of levers. This is how we need to attack it. Now, we don't need to evaluate. We do not need to. I could tell you that the torque of all of that is 5 times 196, which is 980 Newton meters, but we don't need to. Have a look. We're just solving for R1. We can cancel those out because our angles are both, you know, if we were told a horizontal beam, instantly, boom, those angles cancel. Have a quick think before I move on. If our beam was like that, yeah, what do you think we could do? We've got phi and we've got, I'm bad at maths, 180 minus phi? No. They would be, the sine of those two are equal, aren't they? Yeah. So even on a tilted beam, those two angles would cancel. Nice little pub quiz question. No, it's not a pub quiz question. It could be a a test or an exam question. They actually cancel out. It's like the sine of 100 is equal to sine of 80. Sine of 160 is equal to sine of 20. Okay, so they cancel out. Let's keep going. We could do this scenario on the moon because it does not matter. Gravity affects the product of both sides. Look what we get. We get R1 M1 equals R2 M2, and it's almost looking like a centre of mass question. What are we solving for? R1 equals R2 M1 on M2. Throw everything in. 5 by 20 on 10, I think. No, hang on, I've stuffed this up. 5 by 20.
5 times 5, that's 10. Isn't it M2 on M1?
Oh, wait, I put 20. Is that right?
Yes, 5 times 5 is 5 by 10. M2 on M1, isn't it?
I'm going off script. Where did you get 5 from?
Then it'd be M2 on M1.
Yes, it should be R1 equals R2 M2 over M1.
Ah, thank you. My bad. Yeah, okay. I just over 10. Bad at maths. 10. Is it? 100 on 10, 10 meters. Sorry guys, my example, it was a 5 kilo maths. For some stupid reason I went 20. My bad. I was saying even a year 7 could solve this and I was giving you the wrong bloody answer. That was if it was a 5. If it's 20 at 5, then 10 would have to be at 10. Such that 5 times 20 equals 10 times x. My bad, I went off script. Now, thank you. We can then solve for the vertical force. The sum of all forces in the y equals 0, which is weight 1 plus weight 2 plus Fr. They sum to 0. Here we do need a convention. Remember, negative, negative. The reaction force has to be positive to keep this in equilibrium. Okay, so I'm a rearrange first kind of guy. I'd go Fr equals negative weight 1, negative weight 2, and I would get my double negatives. So you get negative by negative 98 minus negative 196 gives a double positive 294. Remember, don't ever leave it your direction as plus or minus. It's 294 newtons upwards. Okay? Now, we could have done that first. In this diagram, we had 2 weights that were known, and so it was only one unknown. We could have solved that first. It wouldn't have enabled us to solve for R, however. We had to use rotation. In most scenarios, you have to do rotational first, and we will get to, in the next 20 minutes, or 10 minutes, we should hopefully get to an example. Over the page. I'll give you guys 5 minutes to do this one. Let's use the larger box to be the larger child. All right. Now let's just say that the weight of the center of mass of the plank is at the center. So again, it generates no torque. So we just ignore it for now. The 20 kilo kid is 1.2 away. Okay. So again, if you assign M1 and M2, then you've got R1 and R2. But please, if you haven't already, write all the same junk out. Sum of all torque equals 0. Torque equals RF sine theta. Clockwise moment equals anti-clockwise moment. What comes next? Take pivot about P. Oh, it hasn't been identified. Let's identify it on our diagram. It's there. Okay? Same deal. M1, I'll try that again. R1, M1G sine theta equals R2 M2G sine theta. it simply becomes a ratio of the masses. What do we get? 1.2 by 20 over 32 gives 0. What? I didn't solve this. 0.7. 24 on 32. 0.781? 0.750. Huh? 0.75 meters. Okay? All right. Now, 0.75 to 2 sig fig because of that one, but we're not really worrying about science inquiry skills. This one's tricky. Now let's, for some stupid reason, let's put the plank off to the side so that its weight does, and let's call that weight plank. There is a center of mass of our plank, right? So now its weight produces a torque. So the clockwise moment is both the weight of the plank plus a child sits 4 meters, a 20 kilo child is sitting over here. All right? So that's the weight of our child. Now, we've been given the entire length is 5 meters. A kid sits 4 meters from the left end, so he's 1 meter from the right end. It's placed on a pivot 2 meters from the left end. So the last thing we need is the distance to the center of mass. Who's good at maths? If it's uniform density, then the center of mass is 2.5 meters from the left. The pivot is 2 in, so what are we missing? A half. All right, so you've got to, they will sometimes give you these nasty little puzzles that you have to do some little arithmetic to get your unknown distances first. The question is, what must the mass or the weight be to balance? Okay? So obviously if it's too heavy, it produces a greater anti-clockwise moment and it would rotate anti-clockwise. If it's too light, then the other two objects, which are producing our clockwise, so we've got 2 clockwise torques producing a clockwise moment. They would win and the system would topple clockwise. But we're trying to balance it, so we write all the junk out. Sum of all torque equals 0. Torque equals, that I didn't mean to write that. Torque equals RF sine theta. Clockwise moment equals anti-clockwise moment. Taking pivot. About P. Where is our pivot? There he is there. Now, here's the problem. We have to do this one first. There is a reaction force. So currently we have 2 unknown vertical forces. So we could not do step 2. Don't highlight this. I'm going to undo it in a moment. We cannot solve the vertical translational first because there are 2 unknowns. Here's the trick. It is a nice, clever, nasty, nifty little trick. If we set the pivot where one of the unknown forces is, then it produces 0 torque. And so if it produces 0 torque, then the rotational equilibrium will enable us to find the 4th force. So we can do that. We set the pivot there, and conveniently that generates 0 torque, so it doesn't play any role in that equals that. And so our unknown force, when we analyze rotational equilibrium, becomes our unknown. Let's write everything out. Firstly, I'll go R question mark M question mark G. Oh, hang on. Let's go clockwise first. Sorry if you've... Come on. Clockwise first, please. We'll go R plank M plank G sine theta plus R child M child G sine theta. That is the clockwise moment, the sum of the clockwise torques produced by the plank and the child because they're on the right side of the pivot. That means that R question mark unknown mass times gravity sine theta must balance that. Okay? Now, you could put sine 90 or you could cancel them out. Let's just evaluate this first. The clockwise moment sums to 490 Newton meters clockwise. That means that when placed 2 meters away, the unknown mass must also produce a 490 anti-clockwise moment to balance. Okay? So our M is going to be the clockwise divided by Rg, or 2 by 9.8. The mass becomes 25.0 kilograms. That is the mass that would produce rotational equilibrium. Now, I apologize, I want to solve in the last... Oh, why did that just move up? Hang on, Control Z. Something happened. I just want to move this across because now... Bracket, you can come too. Come on. Now we have our unknown. We now know the weight force. That's going to be 25 times 9.8, whatever it is. We can now do rule number 2. So in the last 2 minutes, red please. Thank you. Rule 2, we can now sum the verticals to 0. That's going to be weight unknown plus FR plus weight Planck plus weight child. Again, all the weights are going to have a negative. We're assuming the reaction force at the pivot would be positive. So FR equals negative weight question mark, negative weight Planck, negative weight child. So now negative, what do we say, 25 by minus 9.8 minus Planck was 20. And so too was the child. You get 3 double negatives, all producing plus 637. Okay. So that is the force that the support has to push upwards with that magnitude to prevent everything accelerating downwards. If it was any less than that, the Planck starts to accelerate downwards. If it was any more than that, the Planck starts accelerating up into the air. Okay? So here was an example, and most of them you have to go step 1. In fact, I'll just identify step 1, solve for your rotational. Step 2, solve for your translational. Okay? However, I just want you to do for homework Chapter 3.1. All right, which doesn't even mention rotational equilibrium. It's just what's the torque if a force of 10 newtons acts 3 meters from the pit, blah, 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 at an angle of 90. RF sine theta. Okay? Cool beans. If anyone did do that Kepler's third law, leave it here. I've got a free period. I'm going to mark it and give you feedback. Cool? What the hell's that? On the other side.
It's a mistake.
A mistake. Okay, all right. Cool. All right, guys. Thank you very much. I hope you found that